And when I start the recording, I guess that also means that we're starting class. And I see a person frantically raising their hand at the back of the class. Okay. And so let's see. So the question was answered. Are there any other questions? So keep an eye on it. So first thing I would say is always keep an eye on Canvas. A couple of folks seem to have been surprised about the due date for the homework. Always keep an eye on that, look at it and be mindful of it. So, you know, it's like, so it was due at midnight, which is sort of by the 10th, but you know, some people, when they saw the 10th on the slides, they thought it would be sometime during the 10th. And so just make sure that you're always looking for that. You know, the thing, I got some emails late and I was not available to respond to them last night. So it's like the assignment's been turned in. And when the assignment was turned in, it sort of gives me the opportunity also to share like in this particular case, difference equations, there's a lot of steps, right? They're kind of like differential equations. There's a lot of steps to solving differential equations. You have to solve for, get the form of the equation, plug it into the differential equation or the difference equation. You have to do that a couple of times and then in the final analysis, you then have to solve either a linear system or an equation to get the unknown coefficient. So yeah, we'll go over that again. That's just to kind of do that. But I also will point out that in the announcements, you know, I've got a video that goes through where I solve and I kind of talk out all of the different stuff about the homework 3 difference equations. Now you're gonna, I think there's a quiz currently available. Like I think it comes available as class starts, and we'll look at that quiz. There's going to be difference equations on there. I think there are 2, and you know they're different, but the technique for solving a differential equation is generic. It doesn't, you know, the numbers that are there are not really. It's the method by which you apply, by which you solve it, which is important to learn and master. So I'm going to point this out as available to you. And I'll also point out that the quiz is available and it's average, score to keep, average of your attempts. If you get 100 on your first attempt, as strange as this might seem, you might not want to try again because it might actually bring down your total score in the end. It's an average of your attempts. Once you open that quiz, you have 60 minutes to complete the quiz. And the number of attempts that you have is 3. So that's the number of attempts, and the score to keep is the average. And so, you know, I always try and publish, you know, how you are going to be scored. Apparently Canvas hides this information that I can see here from you when you take it. And so I always make a practice of trying to be very clear as to how you're going to be scored in the final. And this one's actually not the highest. A lot of times it's the highest and people get very surprised when it's the average. So I want to be very clear. This is an average of your scores. All right. Let's see, it's due February 13th at midnight. So I'll say February 13th at midnight because that's exactly right. There's no, you know, no confusion is possible. So be aware that that's sort of on the weekend, I think. February 13th midnight is like sort of Sunday night midnight. Gives you plenty of time to make 3 hours available and take the quiz. Is there any questions about that? And there is difference. There are difference equations on here.
Talk about the midterm, just reiterating, it's like you said this before, as far as using MATLAB on midterms, you said no existing code whatsoever, or
like yeah, so let's be very clear about that. That's a great question. Thank you for asking. So these MLX files that you see here, like these guys, you can pull up these MATLAB files. Just like and use them, right? So you can have those on your MATLAB, right? That comes directly from our lecture. You cannot prepare your own MATLAB scripts. You can't come in with a handful of, this is how I solve difference equation scripts.
Like previous homework scripts that we've written.
You can't, so to be clear, you can only have this.
Okay.
You cannot have anything else. And so when I say this, even that's somewhat ambiguous. And in the spirit of being completely clear, we have this PDF, which is lecture notes, like all these slides, and the MLX files, and there's lecture notes, like these notes and all that stuff. So I do not want people pulling up video content and having Dr. Willis like disturbing the entire process. So I really want to deter you from pulling up videos. But yeah, that's what you have available. It's like basically the course materials. Yeah, nothing else. There's no going out to YouTube and watching, I don't know, super difference equation solver 5, go through and solve difference equations. It's not available to you. It's just this, and so, but there's a fair amount here, and I also give you like an index, because this says lecture 1, lecture 2. It's like it's not readily apparent on the surface of this what stuff is where. So I've been, maybe I'll put it in Canvas, just like a page you can go to that lists lecture 1 has this in it, lecture 2 has this in it, lecture 3 has this in it. So if you're faced with, say, an IIR convolution, and you're like, well, okay, I've totally forgotten that. If you know what the problem is, you can say, okay, what lecture covers convolution? And it'll be lecture 5.pdf. And then, so there'll be a list that kind of gives you that lookup table. It's not expansive. It just basically is the title of the lecture, and maybe, like specific if there's a specific topic in the lecture, it's not in the title, it'll add that. But it gives you that way of kind of indexing concepts to these PDFs so you can more easily navigate that information. And that's so it's that one thing in all this, all this information in some way to index it maybe a little bit more efficiently. Yeah.
So I can read code fine and the graph fine, but can you remind me what you're doing again in there with the text and stuff like that?
Yeah, well, it's I try and make things mathematically appear, like the math shit, like the textbook would write it, right? And so I don't know. So in the academic world, when we write articles, journal articles, papers, research, you go to conferences and all these things, the common way of actually writing all that stuff is, as you mentioned, called LaTeX. And LaTeX is a text processor. It's not really it's a different way of writing a document. It's kind of like a programmatic way. And it came actually from Donald Knuth, which is a famous guy from MIT, that kind of thinks of creating documents like typesetting, like when they create the Duke Gutenberg Bible, they take out special letters, and there's all sorts of ideas about how letters should be formed when they're next to each other and things like that. So having said that, I try and make the graphs look good and so is your questions about the stuff here in the MLX files, or is there in the actual plots?
So the actual MLF file, that's fine. Totally agree what you're saying. There was a part, I think it was moving some. There was just some like floating variables with N and N, and I don't know if that was like something you're using for the attack and that should be ignored. Yeah,
there are some of these MLX files which I just have a bunch of LaTeX that I needed to put into my slide stack. Like this stuff, you can see it's just kind of, I'm writing out the definitions, and I'm actually going to be taking those equations and putting them into the slide stack. So there's sort of a take them or leave them kind of thing. If you ever needed for some reason to write a report, you can double click on the equation and just copy this, and you have the LaTeX. What's that? Yeah, if you ever, for some reason, maybe you're writing a report or something, any of these equations you can just double click on and you'll get the LaTeX for it. So, if you were in a pinch and you had to write down, say, complex sinusoid, you could just copy this, right? And you'd have the LaTeX. And by the way, I want to also say for those, this is not, so LaTeX is becoming sort of more widespread. In fact, I think in Microsoft Word, you can paste a LaTeX equation in and it will make the Microsoft Word equation equivalent. So if you are Word users and you hate doing equations, you can also kind of freely copy. I don't want to say pirate. I give you full permission to take these equations and use them in whatever context you might need for your Word equations or LaTeX equations or whatever. And there are some real nasty equations in all of this stuff as we get along here. That's so I guess that I don't know if that answers your question, but it kind of. Yeah, and you'll see. I thought you might also be bringing up like stuff like this, like in this continuous signal plot. I actually have LaTeX right in my MATLAB code. And I thought you might have been referring to that because that actually allows me to see this capital, it's microscopic, I'll try me. You can see sign of capital omega there. So that's kind of hard to get, like, unless you use like the LaTeX in the MATLAB and then you give it the right. So there's syntax in MATLAB to actually make your plots have the mathematical notation in them. And that might be useful if you're preparing a report or something where you want to have plots and have them have mathematical stuff in it. In which case, the code isn't actually as simple as you might think. You do this, but then at the end, you have to like have a special parameter that says use the LaTeX interpreter to interpret the string that I wrote before, so that when the interpreter sees this $sign /omega t $, it converts that into this sign of capital omega t. And so there's some fancy like MATLAB stuff going on in the MLX files that might be at some point, if you ever have to prepare reports with math and that kind of stuff in them. It can be kind of hard to do. And it gives you at least a path. You could just take Dr. Willis's code, copy it, and kind of change whatever you need. And so you could take, wherever's between those $signs is a math equation. So you could take any equation out of any of the slides, put it in between the $signs, and it would render that equation into the graphical plot from MATLAB. So we're getting a little bit far afield and we have much to cover. So I'm gonna go on from there. Are there any other questions? Okay. So, again, we're in lecture 6 and in lecture 6, we kind of skipped over a few slides to get at the difference equation stuff, but we'll revisit those intermediate slides. We talked about difference equations, and this is the form of a general difference equation. And then we talked about a specific difference equation, which was this one right here. This difference equation. Remember, a difference equation is just an equation that involves terms in delayed forms of y and delayed forms of x. Just like a differential equation is an equation that has derivatives in y related to derivatives in x. So, they're analogous. We solved this one by inference and we came up with this as our solution. Then we looked at a way to write these equations with block diagrams. And so I didn't go over this in detail, but you can see that here are the coefficients, right? There's a 1 in front of the y. It's a 1 or an alpha in front of the y of n minus, or minus alpha in front of the y of n minus 1 term. You have these sort of amplification terms. These are the terms that are out in front of the signals. And so if we were to write this as a block diagram, each of these terms that is in front of one of the signals is one of the amplifiers, right? So in this case, A0 is 1. So you can think of A0 being an amplifier here having value 1. There's no such amplifier as necessary because it's not, you multiply by 1, you don't change the signal. Sorry, that's B0, that would go here. This would be B0 equals 1 because x of n is multiplied by B0 and then added to x of n, which is multiplied by beta and then delayed by 2, right? So this is beta, this here is B2 amplifier. This does the delay by 2. And then these two lines come up here just to make sure that that term is summed. And that's also summed with, now why is the term here positive alpha? Is that a mistake? Because we have negative alpha here. That's right. You have to put it on the right-hand side of the equation. Since we have it on the right-hand side of the equation, the sign flips. And when the sign flips, so this is the correct term for A1 in terms of a feedback term and the delay element of -1 to get the difference equation. So this is the right block diagram. And of course, it's an order 2 system because we have the delay of 2. So, yeah.
Real quick, is the Z to the N, is that just the standard delay notation? Or like we're to draw our own block diagrams?
Yes, so if you want a delay of an arbitrary value, it's Z. So if you wanted to enact a delay of N naught, you would pass it through a block that looks like Z to the minus N naught. Right, and that, so if you pass X in, X of N in, then X of N minus N naught comes out. Makes sense. And further, you can give it positive, like if you want to advance it, you can give it positive values, right? If it was Z to the 1, X of N plus 1 would come out. Right, it's not, I mean, it's generic delay, it could be advancing, you know? And so that's the deal with that.
You don't see that often?
Yeah, you don't see that very much. So you don't see that very much simply because you can't construct a system that would depend on future values of the input. So any real-time system or any system that's actually accepting real inputs can't have that in there. But having said that, any system that is not causal, so say that you had a 10th order difference equation, or say you had something that required the value 10 times in the future, right? So 10 samples in the future, like maybe y of n is equal to x of n plus 10. This is not causal and it requires, so y of 0 depends on x of 10, which is 10 samples in the future. How can I make that causal? I could write g of n is equal to y of n minus 10. That's equal to x of n. Right, I could just take that system and actually delay the entire system. Right, and so just make the output that I consider to be the output 10 samples later, and that's actually the input at the x of n at that time. So any non-causal system can be made to be causal by just sufficiently delaying it so that the most, advanced value becomes the current value. And that's basically how. So that's why there's latency in signal processing. A lot of times the best filters will depend on future values and past values. And so we want to, because say they want to interpolate the value, right, of a function at some point. Well, we need to know values on one side of it and values on the other side of it. So you can't really interpolate it until you get the next value in. Otherwise, we're biasing by previous values rather than having values on both sides. So more often what happens is you wait for the additional values to come in, then you calculate your interpolation or your new value, and then you output that value, but now it has a latency or a delay. All right. And so most signal filtering operations induce a latency or a delay. And the idea is typically what you're seeking to do is to get the best numerical performance with the smallest amount of incurred delay. So that's for example, if you're trying to interpolate, or say you're trying to calculate curvature, right? Curvature is like second derivative. So curvature, in terms of, it's the difference of the difference, right? So if you do x of n minus x of n minus 1, we know that's the first order difference, right? That's the derivative. Well, the second order difference is the derivative of the derivative, right? So then we take that, we take minus x of n minus 1 minus x of n minus 2, right? And we get this term that's x of n minus 2x, so this should be a quantity, minus 2x of n minus 1 plus x of n minus 2. And that's the second order derivative. Now that is symmetric about x of n minus 1. You're actually calculating the curvature at x of n minus 1 here. And this is causal, but if you wanted to calculate it at the current time, this would be x of n plus 1, this would be x of n, and this would be x of n minus 1. It would be symmetric on both sides. So it's an example of, say, hey, I want to calculate curvature. Well, I need to take a value in the future into account to see if it's going up or down there, and I have to take a value in the past into account. But this is a causal form of that filter. And the actual curvature output is one sample delayed. Like we're calculating the curvature for x of n minus 1 at the value n. Y of 0 will be the curvature of x of minus 1. Y of 1 will be the curvature of x of 0. Like the curvature that we're outputting has a latency of one sample. Right. All right, so I'm going to go on if there are no other questions. Okay, so relationships. Our previous lecture and a half was on sample domain representations of linear time invariant systems. In the sample domain, we represent a linear and time invariant system as h of n, the impulse response. This lecture is about representing linear and time invariant systems and other systems, because remember, difference equations are linear and time invariant only when they have 0 initial conditions, with difference equations. So what is the relationship between the two? Well, the relationship is that you can get to one place from the other and vice versa. You can go from a impulse response, h of n, to a difference equation. And you can go from a difference equation to an impulse response. Right? In fact, the way, how do you go from a difference equation to an impulse response? Does anyone remember? The solution.
Oh, I know. Oh,
Go ahead, Eric.
so wouldn't it be the difference between the unit step and the subtraction of a delayed unit step? The definition of the delta?
It is the output of the system when you input a delta function. And a delta function I can write delta of n as u of n minus u of n minus 1, which is a very creative way of, because this is, you can do, that's what you typically do in 3111 if you wanted to get the impulse response. You compute the step response and you take the continuous derivative of it. That's one way to do it, right? How do you know that's going to be right? Well, it's linear, right? And differentiation is linear. So if you calculate the solution when you input a step function, that means if you apply the derivative of the input, then the derivative of the output will be there, which is the impulse response. That's the rationale behind why that technique actually works. So you certainly could do that. You could say, I'm going to input the delta function, but I'm not going to input the delta function itself. I'm going to input the step function, get the output. And I'm going to input the step function delayed by 1 and get the output and take the difference of the two. By the way, if you have the input of a linear time invariant system for the step function, say I said the output of a system. Oh, that's the wrong thing to unplug. Well, okay, no. Say I say u, if you input u of n, say I say some function f of n comes out, right? So if you input u of n to a system, f of n comes out. And the system is linear in time of invariant. What if I input minus u of n minus 1 into the system? What will come out?
F of n minus 1.
That's right. That means you only have to solve this problem once. You solve it, you'll get f of n, and then all I have to do is in the solution, is plug in everywhere where you had n minus 1. Then you'll have f of n minus 1, and you subtract those two, and then you have the final solution. So if you haven't, so I think that you're exposed to this idea in 3111 and maybe even in 2254. But since it's been brought up, I'm sort of reminding you that these techniques also all work in the discrete domain as well. Nothing has changed.
And Dr. Willis, just to reiterate this, so that delta of n is equal to mu of n minus 1. Those impulses right there have weights of x of n and x of n, right in front of it. I don't know if that's making sense.
In this particular case, I'm just writing the delta function a different way. Like whatever I'm writing here is the same as what I'm writing here. In this,
Gotcha.
So I'm just trying, so I'm just saying that you can represent the delta function like this and then do, you know, whatever technique for solution. Like if in a, so for example, in this technique for solution, we let x of n equal delta of n. We could let x of n equal u of n minus u of n minus 1. In this particular, if we take that path in this particular case, we'll end up with a lot of arithmetic to do, a lot. It will not be a path to a more efficient solution. But will the solution be correct? If we do all of our arithmetic correct, then the solution can't not be correct. It will be correct. It is mathematically inevitable. There will be a lot more math. You might even end up getting into a place where you have a non-closed form solution because of the path. But the actual solution is the same. So let me point something out, that we have a way. So if we have the impulse response, the impulse response is what we calculate when we find in step 1. So in step 1, we calculate the homogeneous solution. The homogeneous solution to a difference equation is its impulse response. And the homogeneous solution to a differential equation is its impulse response. They also call it, has anyone ever heard the term natural response? Why, did anyone ever wonder why that term exists?
Because it's a natural response to a physical phenomena, I'm assuming.
Yeah, it's literally this is what would happen if you change the state of a system instantaneously to a non-zero value, and then you left it alone, like nothing else happened. For example, we all know that on a first order circuit with a capacitor, that's a first order differential equation, and its impulse response is a decaying exponential. You do it in lab, and you do it in 2254, and you do it in 3111, you get an exponential decay. What's the decay? E to the minus t over RC, right? That's the
time
right.
constant.
That's what it's the time constant, right? The time constant of that is the natural response of a capacitor. If you charge it up to a value and then you let it go, that's what will happen. That's what the natural world does. So the natural response is in fact the natural response of the system in the absence of any excitation. That is, so you can't get more natural than that. That's also why they call E the base of the natural logarithm. This is a naturally occurring phenomenon. This number 2.781 whatever solves all continuous differential equations. That's really weird, but that's what our natural world says it. That's what we observe. This is what science has told us. Yeah.
Do you see natural responses as being like periodic, or just any kind of
There can be
response?
natural responses that are totally periodic. For example, the LC circuit. You would give it an excitation and it goes on forever because there's nowhere for the energy to go. It's perfectly captured. It's either being put into the inductor or it's being part of the capacitor's oscillatory response, right? You have LDI/dt, CdV dt. So when you studied the LC oscillator, you were given a second order circuit that just involved a capacitor and an inductor. And you found that the solution to that differential equation is a sinusoid. And the solution, so if you give that a non-zero value, in fact, that's how clocks work. That's how your clock on your computer, it's an LC oscillator, it's a quartz crystal, it's photovoltaic. Yeah, this is important stuff. This is like how these things, devices around us work. We use this stuff. Crystal oscillators, photonics. This is big time, super important stuff. So yeah, natural responses, there can be really complex ones. And there can be oscillatory ones like the second order LC circuit. There can be ones, any first order system will have energy dissipate. So it'll just be an exponential, decaying exponential of some sort. So
a mass spring system is also part.
Yeah,
right?
Once you introduce both a resistive or something that will release energy into the environment and something that will hold energy, you then get a damped oscillator. So the thing that holds energy will allow that energy to continuously course through the circuit. The thing that releases the energy, the resistor, is going to allow that to dissipate. So then you have a combination of the exponential and the oscillatory. So then you got a damped oscillator, you have a sinusoid that damps over time. So all of this stuff makes perfect sense. doesn't it? I mean, the resistor is releasing energy, so energy is coming out of the system. It can't perfectly oscillate. It can't. It's not. So because it's perfect, it's not. It's being released. It's just going elsewhere. It's heat. It's loss. And so if we had something else that was measuring the excitation of the air in the vicinity of the resistor, that energy will be represented, and you can capture it as a sort of a what they call the multi-physics. So your heat is coming out and it's going into the air and it's captured there, and then the heat itself of the air is changing and you're capturing that energy. That differential equation would reflect that. There's so-called conservative differential equations. Yeah, anyways, we could talk about that, but that has nothing to do with what we want to do today. But this is just the fundamentals of engineering and what all this terminology means. This is good stuff to know before you leave to have careers and things like that. So we were talking about the connection between impulse responses, or the sample domain representation of a linear time invariant system, the H of n, and difference equations. And we have an equation that relates the two. That equation is the convolution equation. So the convolution equation is what relates the two. And this is it. This is the convolution equation. Okay, so the convolution equation, it's got a H and it's got a X. And of course, H is just, if H is a FIR system, or even if it's not, it's just a bunch of it's a constant, it's a function. If I know its value, I can put its value in here and I have something that only involves X and Y, right? In the simplest circumstance, it's a finite impulse response system, right? In which case, Y is a function of only X's. And so in this particular case, we let it be finite impulse response. There are two values that H takes on, -1 and 1. It takes on the value -1 at 0, and it takes on the value 1 at 1. And I can get a difference equation from this impulse response. All I need to do is plug in the values of H, and once I substitute those constants for values of H, H goes away. It's no longer there. Yeah.
Are they supposed to be both positive ones?
Well, I don't know. If we find a typo eventually, let me get to the point where we can verify there's a typo and then we'll fix it. So H of 0 would be multiplied by X of n, according to the equation here. So I simplified the bounds to go from k equals 0 to 1, because that's where our signal in doing H of k times X of minus k. And if this were a k and not an n, it would only exist from 0 to 1. So it simplifies the bounds of the sum to only involve k equals 0 and k equals 1. Then I plug in for the two values of k. I get H of 0 that times X of n minus 0, which is the first term, and H of 1 times X of n minus 1, which is the second term. And now I have H of 0. Well, H of 0 is in fact this number here. It's -1. So in fact, there should be a minus here and a plus in the other case. So what? Well, this one, it looks like this one says 1 and this one says 1, and then this one has a sign difference between that. Well, to make the slides correct, I'm just going to go ahead and I'm going to put a plus here and a minus there and a minus here. Okay. In that case, what's written here is correct. Okay. So there was a typo in the slides, but we've resolved the typo. Is everyone okay with that resolution of the typo? Okay. And so that's how we come up with this equation. Now, in this particular case, we have A, B, and C, and it goes from -1 to 1. And we have A that's associated with the -1, which ends up, because we have an X of n minus 1 in the convolution equation, it's -1. So that's why it comes out as a positive delay. And this is the associated difference equation. Oh, sorry. This is the associated difference equation. So if we have a filter, can we get a difference equation? Yes. If we have a difference equation, can we get a filter? Can we get an impulse response, so to speak? Yes, it's the solution to the homogeneous part of the differential equation, or the natural response of that differential equation. There's really nothing natural about digital, so it's kind of a misnomer, was taking the natural response and saying that in DSP, because, well, it's DSP is a natural, but it's you were sort of operating everything. It's not. It may be less natural than the, if you were to sort of think of it as a representation of the real world. Any questions on this before I go on? Okay. Yeah, this whole notion, like this whole discussion that we had about the interpretation of the natural response is a little bit less applicable when we're talking about a discrete signal inside of a computer, but it is, I guess still valid. Okay, the equation shows the relationship between consecutive values of a sequence and the differences among them. You can rearrange them in a recursive formula so that system outputs can be computed from the signal, from the input signal and past outputs. So I think all we're really trying to say here is that this is how we write mathematically difference equations in terms of that summation. But when we think about calculating the output at a given time, we always kind of think about just y of n is equal to, and then moving all of this term and this term to the other side. So you can think of, if I need to calculate the output at time n, it's a function of, previous outputs and inputs at this time and inputs at previous times. And is this system causal?
Yes, it is.
And that's because everything that y of n, the output at time n, only depends on smaller values of n, right? All of the stuff on here is either n or something less than n.
So a system is causal if, like, one of those said 7 n y n plus 1.
If this were n plus 1, then y of 0 would depend on y of 1, and so that would be not causal.
Okay, thank you.
Yep, you bet.
Well, this possible, we have to take an equation like this, but that's instead of n minus 1 to n plus 1, and we have to shift everything into this one.
So you won't typically be given a problem like that, but because it sort of introduces an unnecessary additional like element, and then so to actually solve that correctly, you shift it to be causal, and then shift it again to be not causal to like technically solve the actual question. So I like to differentiate. I don't like to test those two things at the same time. I like to test them separately. So I will not ask you a question that involves, because everyone will shift it. Maybe I choose that. So then when you ask a question like that, the problem becomes this. You have to choose, say that all the terms in y were shifted. You have to choose one of the y's that's going to be the one that you care about. Say that every student makes a different choice as to which y they consider to be the output. Then you end up getting, well, in this case, at least 3 different kinds of solutions, and at least it introduces unnecessary confusion. But the fact that you understand that you can do that is wonderful, because that unto itself is a good learning outcome. So yes, you can do that, and because it's time invariant. So we could shift any one of these y's and solve for that, and then take our solution, shift it back and get the right answer, because it's time invariant. And so that's great to see that, but I will not ask that because it's just too confusing. We're confusing different topics. Okay, so in continue, so CT stands for continuous time. We talk about differential equations. In discrete time, we talk about difference equations. And so this is something obvious. We've harped on this for a while. We did the technique of induction already. And so here I'm showing the technique of induction formally as a lecture slide, where I say y is a function of a prior value of y minus alpha y of n minus 1 times 3x of n. So this is our difference equation. Then I say, well, let's see if we can get the impulse response. All right, so the impulse response, so the question is sort of get h of n from the difference equation. right? That's what this is solving. Well, to do so, we let x of n equal delta of n, because we know that the output y of n will then be h of n, right? Because it's the impulse response. We put the impulse in and h of n comes out. So we do that. And so when we do that, we come up with we rewrite the difference equation in this way, which is just taking this term and moving it to that side. And then we just plug in values of n. So we know that y of n is equal to 0 for all. Is everyone familiar with the upside down A for all? Okay, so this means for all. Having a, so I've taken a lot of math classes, so I almost write this without thinking about that. But this is for all values of n that are less than 0. So like you have a system at rest, it just is so I try to always be clear about what this means. So we have initial conditions. We know that y of net minus 1 is 0. And that's always the case for when you're calculating the or the impulse response. So we plug in n equals 0. For n equals 0, we have y of 0 is equal to 3 delta of 0. So that's 3 times 1 plus alpha times y of minus 1, which is alpha times 0. So we get 3. Now, for y of 1, we have 3 delta of 1. In fact, for all subsequent values of n, you have delta of a non-zero value. So this term will just not be part of it. Therefore, you have alpha times y of n minus 1 for all these terms. So it's alpha times whatever y of 0 is. So it's 3 alpha. Then it's alpha times 3 alpha. Then it's alpha times 3 alpha squared. So you generally see that you'll get 3 alpha to the n times u of n is the output by induction. By just looking at the pattern starts at 0. So that's how you get the u of n. And the pattern is that you always have a 3. So that puts the 3 in there for every value of n. And there's the power of alpha is actually, you can see this is alpha to the 0, alpha to the 1, alpha to the 2. So whatever value is here is actually going here. So more generally, if we go on to sample index n, it'll be 3 alpha to the n, u of n. That is the technique by inference. You just kind of see the pattern and generalize the pattern to the nth variable. Okay. Then we have the technique, yeah.
So your input for that question there is delta of n. So
Yeah.
when you get your alpha, you know that's your h of n, your impulse response.
Mhm.
I think like on our homework 3, our x of n, I don't think it was just delta n.
Yeah, so that might be, so this is to get h of n. And so this is the kind of thing that you would do to get an impulse response or homogeneous. This is one way, this is the inductive way to get a impulse response.
Oh, so you're telling it like just delta of n because that's what I'm looking for.
Yeah, so I kind of like this, that's why I kind of, if we want to get h of n, here's an example. So I don't really suggest that so this is a last ditch. This won't work if you have a particular solution, right? In general, this gives you an idea of how the difference equation works. It lets you understand when there's feedback, it's recursive, but this is not how I suggest solving difference equations for a number of reasons. And by the way, if the difference equation has non-zero initial conditions, it's not linear and time invariant. You can't use the Fourier transform or the Z transform to solve it. So I warn you, don't just if you think that you want to solve a difference equation that's given to you on say the midterm that has a non-zero initial condition, you really need to do this. There's not another path. It's not linear and time invariant. Specifically, it's not time invariant. So you can't really just say, I'm going to take the Z transform and solve it that way, which is another path, right? So if you get a full difference equation that has a x of n that is defined as a value, like 8u of n or something like that, you need to take this technique for solution that I provide right here. Right? That inductive method is meant to kind of help us understand how it works. But this technique for solution is the technique solution for solution that I really feel like we need to apply for the quiz as it is right now, like for the quiz that you'll be taking for the next few days, and for the midterm, because it works all the time. It does not care whether or not the initial conditions are non-zero. If the initial conditions are zero, there's a few other paths you can take. But this will always work. Does that help? Yeah. And this is like, I mean, say that you are broken, have it struggling, and you couldn't even get the homogeneous response for some difference equation. You could try this. Right? Because what this is getting your H of n. It's getting your homogeneous response. This thing here is the homogeneous response. If I wanted to if this was part of a difference equation problem, I could say alpha 1 times 3 alpha, so 3 alpha 1 to the n, it would be the homogeneous response, and you'd have to solve for alpha 1. But I do not suggest that. It's a sort of a last ditch effort. What I use this for is to sort of tell us how these difference equations work. Tell us what, and for example, if you've solved one of these difference equations correctly, you'll see that the solution is like some number times 1 to the n plus some number times 2 to the n. You can't solve. I mean, maybe you can solve that by inference, but that's incredibly complex. Like to figure out that, oh, I see the number 5. Well, clearly that's 4/3 times 1 to the n plus, some other number. It's like, I don't know how, if you can do that, maybe you shouldn't even be here. Maybe you should be out making millions of dollars with those arithmetic calculations. But it's really hard to see those patterns, right? When it comes to a second order system. First order systems you can actually solve because you'll just see, these are all first order. This is a first order system. And it'll always end up with something like an alpha to the n like this, right? But second order systems are really complicated to kind of oscillate. There's multiple geometric series involved, and it's almost impossible to decode how those numbers are interacting to get these final numbers. I'm not sure if that, just use this, please. Okay, so when we solve a difference equation, where the solution comes in 2 parts, the homogeneous part and the particular part. For solving the homogeneous part, we know the solution, just like in differential equations, but in difference equations, the solution is lambda to the n. So to solve for the homogeneous response, we take this lambda to the n, we plug it into the difference equation, and then we calculate the characteristic polynomial, right? Now, if it's a first order difference equation, the characteristic polynomial is this d1 over minus d1 over d0. Okay, so yeah. Yeah, y of n, so yeah, this is, oh, I lost my cursor. Yeah, the output, sorry. The y of n is equal to 0 for all values less than 0. It's kind of like saying, think of this as actually a system. Think of it like a numerical beast. You put a number into it and start spitting numbers out. The state of this system is such that all of its output values are 0 up until it receives a non-zero input. That's what this statement means. And then at time 0, we hit it with an impulse, right? That impulse excites the system, so to speak. It makes it start doing something other than zeros, all right? And then what it does after that is termed the natural response, or the impulse response. And that's why we call it the impulse response. And so we need this definition because at this very first value, at 0, we need y of -1. And if we don't have it defined as 0, we don't know what to plug in there. Like this very first value here, it ends up, we plug it into the equation. We have y of 0, that's this term. That's equal to 3 delta of 0. This is supposed to be a delta function. Plus alpha y of -1, right? And so we need this at this point in time. For that minus y of minus 1 isn't defined to us as it stands. And we need this system at rest definition that I just wrote down here in order to know that y at time at sample index -1 is in fact the value 0. So yeah, if I did something like y of n equals 2 so y of -1 is equal to 2 as an initial condition, then at this point I would plug a 2 in there instead of a 0. Does that make sense? And that would correspond to a system that is not at rest. So we are no longer calculating an impulse response. We're calculating a response to a system that's already been excited. So it's no longer a natural response. It's no longer can be called h of n. It's sort of something else. Does that make sense? Like h of n has a special meaning, and it's a thing that you get when the system is at rest, and this is the at rest condition mathematically. When we have something when it's already got numbers in it, so to speak, it's got non-zero values in it, then it's not at rest. So this one here?
Yes.
Okay. So we have y of 3. That's equal to 3 delta of 3. And the big thing to see here is that for all of these deltas, where the delta is, there's a non-zero value inside the argument, all these terms are 0. And then we've got plus alpha times y of n minus 1. Now n is 3, so this is y of 2. And so now we see that y of 3 is just equal to alpha times y of 2. And so since y of 2 was 3 alpha squared, y of 3 is then 3 alpha times 3 alpha squared, which is 3 alpha cubed. Yeah. So in all of these ones that have this y as a function of previous y's, we'll have this recursive behavior, and we'll also have this exponential behavior. That's why we deal with a to the n, the sum of a to the n from 0 to infinity. It shows up all the time, and this is yet another case. Like this is an a to the n kind of thing, alpha to the n in this case. So good grief, I don't know what's going on here.
So Dr. Willis, could we also express the so is it that we started off with 0 because here I'm gonna write here that u of n.
Oh, good grief.
see-
How are you doing that? Stop doing that.
Oh,
Stop
it's
it.
magic.
All
Oh,
right.
but I mean I can clear it though.
That is outside of the lines of lecture.
Oh, I'm sorry because I was online. I thought that I could
Well, that's really cool, but I'd prefer the lecture notes to be a function of the professor only.
okay, okay. So I have a question then. So could we also say that it's starting from 0 because the unit step function can be represented as a summation of delta n functions, and since this is a delta n function, we can say that a summation from 0 all the way to n values, right?
I don't think I follow exactly, but I think that so the step response will be the sum of the impulse response. Is it maybe something I'd like to say that's relevant? But I'm not sure I follow exactly. And please don't erase anything. Certainly, I see.
Oh no, I would never do that. You can only erase what you annotate on Zoom. So in Zoom, there's this thing where you can annotate on the screen, and whenever you
annotating, and you're actually in the.
Yeah, I'm in the Zoom meeting, and for us viewers, there's an option above where it says view options, and we can annotate.
This is sort of a separate thing. Oh, well, that's creative. I mean, maybe
Yeah.
that'll be something we can use in the future, but at the moment, let's
Yeah,
make
yeah, okay.
it only a function of Dr. Willis. I don't know. You're not getting paid, Eric. So
No, I just wanted to get my point across. That's all it
however,
was.
so it seems like this is boundless opportunities for me. But just take that in the right way. Let's see. Yeah, so I think what I want to say here is that this kind of helps us understand how difference equations work. And for sure, we did a impulse response. We could have let x of n equal the the step function, and gotten the step response. But yeah, you just have to be careful. They're tricky. And there is like a special, this convention where we're saying the system is at rest. It's like a special circumstance. Okay. By the way, so we kind of, step 2, like this is calculating the homogeneous response. And I made a claim that the homogeneous response is in fact the response that is the impulse response. So in this case, what is the value of D0 and D1 for this? So we would say that this would be D0 and this would be D1, right? And so remember, like where are these D's coming from? Remember, we're going back to this equation in the very beginning, where the D's are the coefficients of the Y's, right? So realize that those D's, they're supposed to mean something, right? They are the coefficients of the Y's from our definition of the. So D0 would be the coefficient of Y of n minus 0, and D1 would be the coefficient of Y of n minus 1. So when I give you this equation down here, that's the ratio of minus D1 over D0. And I look at this, what's minus D1 over D0? What's D0? 1. What's D1? Negative alpha. What's minus D1 over D0? Alpha. Alpha to the n. Lambda to the n. We just solved for lambda. It's alpha. So you just, you have the solution. Then you have to calculate 3 because that's the alpha 1. It's alpha 1 lambda to the n, right? And if we then solved for that, we would have gotten alpha 1 is equal to 3. So in fact, these two solutions are not different. You can apply them in the first order difference equation, still get exactly the same result. Okay. So, so yeah, if it's first order, you know that lambda takes the value D1 over D0, minus D1 over D0. It's a solution for all first order. That what I'm trying to point out is what's written right here in this little tiny part of the slide. It's a solution to every first order feedback system in Y. If it's a function of Y of n and Y of n minus 1, you actually have the value of lambda there. If it's a function of 2, if it's a function of Y of n minus 1, and Y of n minus 2, then you have a second order system. And you apply this equation, and this will give you 2 lambdas, and you would write it out as alpha 1 plus alpha 2, lambda 1 to the n, lambda 2 to the n, and lambda 1 and lambda 2 will have specific values. Is that clear? So these equations, they're general solutions to first order and second order difference equations in Y. After that, we solve for the particular solutions. This is when the form of x is not the delta function. When x is not the delta function, we need to find a particular solution. Right? And so this is how we do it. We assume that the solution is the same form as the input. And so if you add k times the step function, it would be beta times the step function. In fact, this is actually what you also do when you do the delta function, but it's sort of unconscious. You get a particular solution. Then what you do is you add together the particular and the homogeneous solution. So you do YH of n plus YP of n. And you get the general solution Y of n. Now we know that YH of n will have unknowns in it. If it's if it's a first order difference equation, it'll have alpha 1. If it's a second order difference equation, it'll have alpha 1 and alpha 2. So at that time, you solve for alpha 1 and alpha 2. You had a question? Sure, beta itself could be a complex number. And so the techniques don't change at all. Yeah, nothing changes. If beta were a complex number to the n, it's complex number to the n. None of the techniques actually change if it's complex. But I typically, in the form of the questions I ask, I don't recall asking that for a complex number. But I might, and if I were, nothing in execution changes. It's exactly the same process. Yeah. And so then we went through and we solved this, and we kind of, I'll do this again, but we have, this is a second order difference equation, and it's second order in Y. And so when it's second order in Y, we're going to come out with two lambda values. And that's by applying the quadratic formula or by factoring it. In this case, we factored this directly. All right, we came out with this as the characteristic polynomial. How did we get that polynomial? Well, we plug in lambda to the n, which is the solution that we know is correct. So lambda to the n for y of n, you get this term. Y of n minus 1 is then lambda to the power n minus 1, which is this term. And then minus 6 y of n minus 2, that's minus 6 lambda to the n minus 2 power. Now, all of these lambda have this n power in them. So we sort of factor a lambda to the n minus 2 out of all of them. And that leaves a lambda to the n minus 2 out in front, and then a quadratic polynomial inside. And what's interesting is kind of flips the order, like this lambda to the n, because we took a lambda to the n minus 2, it ends up having a lambda squared, right? So it's a little bit algebraically confusing. You should look at this again. But we're factoring out a lambda to the n minus 1. Well, since this is a lambda to the n in front here, when you factor out lambda to the n minus 2, you have to actually leave a lambda squared so that the squareds cancels and you get back a lambda to the n. That's what's going on algebraically. And the other terms follow. So you have lambda squared plus lambda minus 6. You factor that using either the quadratic formula, or I see what this factorization is, or any other means of factorization. And you see that the factors are lambda 1 is equal to minus 3, lambda 2 is equal to 2. And now you know the homogeneous solution is some unknown constant alpha 1 times minus 3 to the n plus some unknown constant alpha 2 times 2 to the n. And you are done with step 2. Yes.
What about repeated roots, or I think what you might have been asking, like complex roots, like you did.
Oh yeah, complex roots are fine. That just means you got a complex number here and a complex number there. It's all good. That's all cool. No problem. We've got that, right? So when you apply this formula, and something and whatever's inside that square root ends up being negative, what do? You put a J, you make it positive, go on with life, right? Like if this ends up being like if it's a complex number, right? But so just say, okay, well, I see that we have the square root of a negative number. So I'm going to take and I'm going to represent that number as the square root of negative 1 times the square root of a positive number. So you put a J in front of it. And then now you have a complex. So because it's a plus and minus square root here, because it's plus and minus there, you'll end up with a plus and minus J times something. So what that means that whenever you get a lambda that's complex valued, they come out in conjugate pairs, right? One is going to be plus whatever that number is times J, and the other one's going to be minus whatever that number is times J. And that means that you'll have the symmetric pairs in the complex plane. You know, about the imaginary, or about the real axis, because they're reflecting about the real axis. But nothing, but like just like so to speak, like be blind to it. Who cares? Like, so, oh, I see there's a negative inside the square root. I write down J, I change the sign of what's inside the square root, and I just go on.
Same with repeated roots.
Repeated roots are a little bit different, but let's just not get into, let's solve these equations correctly and then get into repeated roots. But so I don't want to get too far afield, but certainly addressing complex roots is something I want to address. Repeated roots are a little bit more advanced. And so I don't think we're ready for that yet. We can cross that bridge later.
Dr. Willis, quick question about the complex alpha values. So whenever we get those complex values, if we were to get complex values, could we then assume that the system will be stable?
No, in fact,
Not necessarily, right?
Yeah, not necessarily. Remember, the
Right.
magnitude of the complex value has to be less than 1. So by the way, is this system stable here already?
Yes, it is stable.
Well, let's see, if I block out -3 to the n, is alpha 2 times 2 to the n a stable system? It grows like with n, right? This is for u of n, like this is gonna be an unstable system. Like with these alphas would need to be less than 1 for them to be stable, right? So yeah, stability is sort of, so if this represents the impulse response, that's an unstable system. If this represents an impulse response, is this a stable system? Now, if the answer has an if in it, if the magnitude of alpha is less than 1, then the sum, if this is h of n, then the sum from n equals 0 to infinity, sum of the magnitudes of alpha would be the sum from n equals 0 to infinity of 3 alpha to the n, right? So as long, what does that come out to as long as alpha is less than 1? 3 times 1 over 1 minus alpha. Only if the magnitude of alpha is less than 1. And that's finite, so it's stable, right? But if alpha magnitude of alpha is greater than 1, this is unstable. So we're kind of solving a lot of problems as we go. So does that, hopefully that all makes sense. The particular solution. So in this case, we have x of n, we have a specific value for x of n. It is not the delta function, it is the step function. It is in fact 8 times the step function. And we know that the format of the output will be the same as that of the input, but having a different value multiplied by the step function that we do not know. So we're going to call it beta. So we say that the particular form of the solution is the same form as the input, but having an unknown coefficient, method of unknown coefficients. We plug it into the equation and we get beta times u of n plus beta times u n minus 1, which is this and this, and 6 beta u of n minus 2 is equal to x of n. Of course, x of n is our input, and it's defined, and we put it in here because this is our particular output due to that particular input, which is why it's called the particular solution. It's the output that's particular to the specific input. Notice the natural solution needs no input to assume a value. It doesn't care what the input is. The input is going to be some stimulus having magnitude 1 at 0, and its output is what naturally occurs thereafter. That's how it's defined. The particular solution is what is output when this particular function gets put in. And this function actually continues to excite the system. So they often call this the forced response. Has anyone ever heard the word forced response? That's because its input is constantly forcing values in that are non-zero, that continuously excite the system and force an output in response to that input. That is the analog, that is the actual meaning of why it's called the forced response. It's this input itself is forcing a separate, completely separate and linearly separable, which is why you can solve it in 2 parts, sequence of numbers that come out. And that's why we can solve this in the way that we do. We have the homogeneous, like the natural response to every single non-zero value that comes in, and then the values that come out because this thing is constantly putting new values in. So anyways, we plug it into the equation, we get this. Now, these all have step functions, and these step functions are all 1 for the times n greater than or equal to 2. So we restrict our attention to only the values of n greater than or equal to 2. Simplifies all of these step values to have the value 1, and it leads to this algebraic equation in beta alone. At that point, we can solve this algebraic equation in beta alone, and we get beta is equal to -2, which means we know the particular response is -2 u of n. So now we know the homogeneous response, and we know the particular response. With that in hand, we can solve the entire system. And so we already have we have everything except my cursor. And so we then go to the final solution, which says, I know all systems that respond to this particular input so all difference equations having this form with this input will have this as a solution. Now we're going to calculate the solution to the specific kind of system whose initial conditions are non-zero and have these values. So we use the initial conditions in order to determine the unknowns alpha 1 and alpha 2, right? And that makes our solution specific. So at this point, we've calculated all solutions to this problem. And now we're just calculating the exact solution for when the initial conditions have this value and this value. Yeah, you cannot solve. So yeah, in fact, if I were to, that's actually the initial conditions. So there'll be, in fact, I might even ask you a question like that, and maybe I already have, where I say that the system is initially at rest. What I'm telling you is I'm giving you an infinite number of initial conditions. And all of those initial conditions say that for any value of n less than 0, the initial condition is 0. So that means you can solve a difference order equation having an infinite number of order, right? Because you have an infinite number of initial conditions. They're all 0. You'll never be asked that. You'll only ever really need to use y of -1 and y of -2 because those are the values that you need when you're calculating the output at 0 and you have a second order or first order or a second order difference equation. Does that make sense? Okay. So in this case, we have y of -1 and y of -2 specified as non-zero values. And so we have to go ahead and use our equation, okay? So y of 0 is alpha 1 minus 3 to the 0, which is 1, plus alpha 2, 2 to the 0, which is 1, minus 2, okay? So note that we're applying, a critical thing is that you want to apply your initial conditions at the time that the input is applied. This input is applied at time n equals 0. It is critical that you calculate your solution when the input is being applied. Otherwise, you'll be solving for a system as if the forced input is not there. And it won't show up in your equations and you'll get the wrong solution. So say that the input was 8u of n minus 1. You have to consider n equal 1 and n equals 2 instead of 0 and 1. You need to consider the time at which the input is applied, okay? Otherwise, these equations will not reflect the response of the true system. It'll be missing the forced response at some point in time, okay? Either any form that's written correctly is okay, so yeah. Remember, we're not. I don't want to be that restrictive. Like if you understand the thing and you write it down correctly, you should expect to get credit. That is written down correctly. It's this function for the values of n greater than or equal to 2. That is written correctly. But I think in a more general sense, like if you write down the solution, it's written down in a correct form that makes sense and uses the theory, then you should get credit. And if you don't, you should come and talk to me about it. Okay. And if you feel that, then we can talk about, if there's some kind of discrepancy, that often is an opportunity to learn something. So if there's some kind of difference between what was graded and what you see, you should always fervently fight for your points. So I have no problem with that at all. And I think it's a sign of a student that wants to do well. And so it's good. I'm not one of those faculty that has a problem with students coming and talking about their grade. I think that's a sign of a good student. So I encourage it. So anyways, we get this equation for y of 0. And we get this equation for y of 1, right? We alpha to the 1 minus 3 to the 1 plus alpha 2, 2 to the 1 minus 2. Okay. And so we have also this y of minus 1 is equal to 1 and y of minus 2 is equal to minus 8. So we can also put in the actual values for this and calculate the other values. So let's see if that's Right, and so how do we go about solving for the other things? This is how we're gonna actually solve everything. So we've solved, these are the equations that we have in the unknowns, alpha 1 and alpha 2. All right, so I'm just gonna try and do this in a, I know it's a little bit late, but this is sort of the critical part of plugging in the. We also have to plug in this value and this value. So what you do is you basically plug in and get this number -41 and this number 55. And the system of equations you need to solve is the two equations that we had before and the values that they're equal to, which is -41 here and 55 there. Okay, how did we get -41? We took the values of, we actually used the equation defined at 0. So y of 0 is equal to x of 0 minus y of -1 plus 6y of -2. X of 0 is 8u of 0, so that's 8. Y minus y of -1, y of -1 is 1, so that's -1. 6y of -2 uses this initial condition, so it's 6 times -8. So we use the initial conditions to determine this number right here, -41. And in the very same way, we look at y of 1, that's x of 1. X of 1 is 8 times u of 1, so that's 8, so we get that. Minus y of 1 minus 1 is y of 0. Well, we have y of 0 is already -41, so that means that -41 goes there. And y of 1 is 6y of 1. Sorry, this is 6y of -1. Y of -1 is 1, so we use y of -1 here. And so that gives us the number 55. So now we have two equations. We have two unknowns. That is this linear system here. And we solve that linear system to get alpha 1 and alpha 2. So that is how you use the initial conditions to get your solution. Because this will give you your alpha 1 and your alpha 2. You can use MATLAB, set it up as a linear system. You can solve it by hand, however you like. I personally like to use MATLAB, and I'll show you how to do that. In our next lecture. We don't have time here. We're already over. So I think I'll stop lecture there, and good luck on your quizzes. And we will see you all on Tuesday next week, where we'll talk about finish up our difference equations and talk about the Fourier transform. Yeah.
I'm a little confused on your general solution. Are you at the unit step of n-2?
Yeah. Remember that back here, when we solved for the particular solution, we restrict, it was only valid for n greater than or equal to 2. No, when we did this, see, we have a u of n, a u of n minus 1, and a u of n minus 2. And so we wanted all of those step functions to evaluate to 1, so that we could simplify it to this equation here. Yeah, and when we made that restriction, on n, that restricts our solution to only be valid for those values of n. And so it's this specific step right here that makes this solution here is only valid for values of n that are at 2 or greater. In fact, the entire solution has a single value at 0, a single value at 1, and then this value for every point thereafter. Yeah, if I had solved this 3 times, one time just using this beta u of n, I would get the solution for only time 0. And now if I were to solve it for this first and second term, I'd get the solution for only time 1. Right?
So this would be good, like on the homework, if you wanted, like on the homework, when it asks for any say 15, or you could find the solution and then jump to.
Well, you could just, so there's a lot of different, so generally most of the time when we ask for those solutions, in fact, all the time, we ask for solutions that are actually past this value of n. We never ask for a transient
So you
solution.
can find that general solution and jump that.
Yeah, our suggestion is to find this and then plug in the value of n.
That's a lot easier than how I looped through it.
Yeah, you can actually iterate the difference equation and try and get to the value of n, but I warn you, because if you do that, sometimes numerical precision will actually give you the wrong value. So this is what we're hoping you will do, okay? Yeah. Yeah,
So Willis, quick question. What time is your office hours end?
actually 10 minutes from now.
They end 10